Today we're going to start to explore what angular momentum is and how it is used to describe rotational motion. We'll see that angular momentum is a vector and, so, as you might expect, we'll need to discuss how we can determine both the magnitude and the direction of this quantity. We'll soon see that the vector operation, the cross product, is involved in defining the angular momentum vector. You'll recall we first encountered the cross product when we discussed the meaning of torque. We'll see here that many of the same ways of thinking about cross products for determining the magnitude and the direction of a torque will carry over to determining the magnitude and direction of the angular momentum. Let's start once again with the system of a particle of mass m that rotates on a rigid rod of negligible mass. This rod is fixed at one end so that at the other end the mass rotates about an axis we'll label as A. Here we imagine at some instant of time the particle is moving with a velocity v, as shown. For speeds much less than the speed of light, we know that the corresponding momentum of the particle is the vector p, the mass m times v. Now, as we know, anytime we describe rotation, we need to say something about the rotation axis. We do this here by means of the position vector r sub a vector p that locates where the particle with momentum p is relative to the axis A. With this position vector and the momentum vector, we can now specify the angular momentum, which is defined as the cross product of r sub a p with p. We recall from our earlier discussion of torque, where we first encountered the cross product, how to find the magnitude and direction of the cross product. To visualize this, let's start by placing the arrows representing the two vectors involved in the product, here r sub a, p, and p, tail on tail. Then, as we recall from our discussion of torque, the magnitude of the cross product is the product of the magnitudes of the vectors together with sine theta, where theta is the smaller angle between the vectors. The dimensions of angular momentum are mass times length squared divided by time, with corresponding SI units, kilograms, meters squared per second. We'll also recall from our earlier discussion of torque that the direction of a cross product will be perpendicular to the plane defined by the two vectors. In this example, either out of the screen toward us or into the screen away from us. We can use the right-hand rule to tell us which of these directions is the direction of the angular momentum. First, take your right hand with your fingers straight and align your hand in the direction of the arrow representing r sub a, p. Now keep your fingers straight, orient your palm so that it faces the arrow representing p. You may need to rotate your wrist to do this, but make sure you keep your fingers straight and pointed along the direction of r sub a, p. Now curl your fingers into a fist while keeping the rest of your hand motionless. Finally, stick your thumb straight out from your hand without moving any other part of your hand. The direction your thumb points is the direction of the angular momentum vector. In this particular case, we see that the angular momentum is out of the screen, toward us. Now this direction of the angular momentum may seem a little weird. However, as we discussed earlier, the axis plays a central role in any rotation problem, so it makes sense to link the orientation of the rotation axis to the direction of vector quantities associated with rotation. You may find it helpful to relate the direction of the angular momentum to the direction of motion in the plane by uncurling your fingers a bit while keeping your thumb pointing in the direction of the angular momentum. You'll find that in this case, and many others, the fingertips of your right hand point, roughly speaking, in the direction of the rotation in the plane. Now for this particular example, we can say a bit more about the angular momentum magnitude. Since the rod is rigid, the mass m cannot have any motion parallel to the rod, or, to say the same thing another way, m cannot move parallel to r sub a, p. This means that p is perpendicular to r sub a, p. So the angle theta is pi over 2 radians, and sine theta is equal to 1. So that the magnitude of the angular momentum is simply, in this case, the product of the magnitudes of the two vectors. This occurs because the rigid rod constrains the motion of the particle to a circular trajectory centered on the fixed axis. We'll run into this again a little later when we talk about the angular momentum of a multi-particle system. For now, though, let's change our example a little by removing the rod. This allows us to consider a case where the mass m has some motion parallel to the vector r sub a, p. In other words, the angle theta between the two vectors will not be pi over 2 radians, and therefore sine theta will be something other than 1. How can we think about the physical meaning of the angular momentum magnitude in this situation? Here again, it's helpful for us to recall our earlier discussion of torque, where we gave two complementary geometric interpretations of the torque magnitude. Let's apply those same ideas to the angular momentum case. First, if we associate the trig function sine theta with the magnitude of the momentum, we can see that this combination gives the magnitude of p perpendicular, the momentum component perpendicular to the position vector. So one way to think of the angular momentum magnitude is as the product of the magnitude of p perpendicular with the magnitude of r sub a p. However, we also have a second way to think about the angular momentum magnitude if we associate the trig function sine theta with the magnitude of the position vector r sub a p. The geometric picture for this is as follows. Imagine drawing a line parallel to the momentum vector p passing through the mass m. This line is called the line of action. The distance of closest approach of the line of action to the axis, or, in other words, the shortest distance from the line of action to the axis is just the magnitude of r sub a p times sine theta. This length, r perpendicular, is the moment arm of p about the axis a. So we can also say the magnitude of the angular momentum is the product of the magnitude of p and the moment arm r subperpendicular. These two ways of thinking about the angular momentum magnitude are equivalent. Applying either method to a rotational motion problem yields the same result. However, again, like in the case of the torque magnitude, we'll find that there will be times when, for a given problem, one way is easier to apply than the other, so it's good to be familiar with both. Let's practice this with the following question. A particle of mass m is located a distance d below the x-axis and is moving with a velocity v, which, at the instant shown, points in the minus x direction. Choosing the origin as the axis, what is the angular momentum, both magnitude and direction, of the particle? Be sure to express your answers in terms of the given quantities. The correct answer is answer 5. We don't have enough information here to specify the magnitude of the full position vector, or the angle theta, so responses 1, 2, and 3 are ruled out. However, by extending the line of action of the momentum vector, we see that the moment arm, the distance of closest approach of this line to the axis at the origin, is simply d. So the magnitude of the angular momentum here is just the magnitude of the momentum, m times the magnitude of v, multiplied by d. The right-hand rule gives the direction of the angular momentum, which is into the page, or equivalently, the angular momentum is pointing in the minus z direction for the choice of coordinate axes as shown. One final note here. You'll notice that in this problem, and in the earlier example without the rigid rod, there isn't anything physically present at the axis, like an axle or a hub of a wheel. It's not necessary to have something physical located at the axis. All we need to specify the axis is to specify a location. Once we have that in hand, we can then specify rotational quantities like torque and angular momentum. There are at least two important implications here. One, we often have the freedom to choose our axis in studying motion problems, but in doing so, we should expect that the value of the motion quantities will depend on our axis choice. You can see this, for example, in the previous clicker question. Keep everything the same, except choose your axis to be a distance d below the origin. What is the angular momentum in this case? 2. Motion problems can have a rotational character even in cases where we don't have obvious rotation about something physical, like an axle or a hub. Our clicker question is a good example of this. This means that the concept of angular momentum can be applied much more generally than you might think at first glance. We'll see how that plays out as we begin to apply our angular momentum principle, which we'll start doing beginning in a lecture coming up soon.